Good evening and welcome to tonight's 6 at 6 lecture. I'm Shauna Riley from the Scripps Howard Center, and I'm pleased to present tonight's presenter and all of the things 6 at 6. So the 6 at 6 lecture series is a set of 6-ish. We have 7 this year. 7 at 6. Lectures where we take NKU faculty into the community to show what NKU does and does well. So we're really excited to be able to show tonight's lecture with Dr. Nutter when he talks about his exploration of the Northwest Territories in Canada.
None of it.
None of it. And I'm from Canada, so I can say we don't want none of it. Sorry, that was really
It's not much there.
Anyways, this is our first of 4 for 25, the spring of 25. So we have another lecture on the 20th of February, the 20th of March, and the 16th of April. So if you are interested in what you hear tonight, perhaps you might be interested in checking out another 6 at 6 lecture, and we'll send you an email to tell you more about it. So thank you for being here tonight, and thank you to the Cincinnati Observatory for having us. And with that, I'm going to hand it off to the incredible Dr. Nutter, who is a professor of physics. I realized I did not introduce him, so we should do that.
Good save.
At Northern Kentucky University. He is going to talk a little bit about his explorations to retrieve a satellite. Ish.
A cosmic ray instrument. Let's just walk through there. I'll tell the rest.
Sounds good.
Thank you, Shauna, and thank you, everybody, for coming. Just checking that the mic was off. Right. So thank you very much. What I want to tell you tonight is the story of how I ended up here in the high Arctic on a glacier on Ellesmere Island in the far north of Canada, stepping off of a helicopter to walk. Come on through. Come on through. To walk out to this detector and start taking it apart and getting it home. Right, this is that story. In the process, I'm hoping to give you a sense of what that process of taking this instrument apart and bringing it home was, why we did it, and a little bit about the science behind the instrument. I want to give you a sense of what the adventurous side of science can be like, right? The field work, right? Not forget about the lab notebooks and the test tubes and the lab coats. I mean, let's get out in the field and get our hands dirty and bonk our head and cut our fingers and all that good stuff that you do in the field, right? This is what this is about, and I hope that you'll appreciate this. Before I get started, I want to thank Shauna and the Scripps Institute for all the good stuff that we've got here. I think I actually have a note of what the actual name of that place is. There it is, the NKU Scripps Howard Center for Civic Engagement. I want to thank Norse Media for providing the technical assistance, and I want to thank the Cincinnati Observatory for this lovely space. It's always a pleasure to come back here and get to talk to the people here and all the people visiting. Well, I want to start by saying, yes, I am Scott Nutter. I'm a particle astrophysicist at NKU. I work on NASA-sponsored projects. I want to point out the difference between a particle astrophysicist and an astronomer. An astronomer uses telescopes, as I use telescopes, but an astronomer's telescopes collects electromagnetic radiation, like light or radio or X-ray or gamma rays. These are all part of the electromagnetic spectrum. Whereas I collect particles from space. Right? These space particles we call cosmic rays, right? Cosmic, outside the Earth, and rays because radiation, right? So space radiation. Whereas astronomers will collect the photons themselves, they also can point back straight and form an image of what they're taking a picture of. I cannot form an image because my particles do not travel in a straight line. And I also use different technology. I use the same technology as you find in colliders in collider experiments. Cosmic ray detectors do not have a cup full of particles at the end of the experiment. The particles go through them. And we just measure various aspects of them as they pass through. They're going close to the speed of light, so we have to be quick about it. But we have specialized detectors to allow this to happen. The Helix instrument, for example, the instrument that we'll be seeing a lot of pictures of, has a suite of detectors. For example, maybe I should use the pointer for the people at home. This top and bottom is a plane of detectors that detects both charge and velocity. In the middle is a giant magnet. You'll see it painted in black in the pictures that we'll show. With a it has liquid helium in it, superconducting coil, has a tracker on the inside. It'll detect the momentum as the particle passes through in a magnetic field. You know that particles bend. The amount of bend is a way to figure out what the momentum of the particle is. And momentum is important. We can figure out the mass of what's going through. There's no imaging in this detector. Cosmic rays are important because they're a free sample of stardust. And what I mean by that is the matter that's created and expelled by dying stars. So we'll talk about this more, but stars are the source of the elements in the periodic table. And there's a cycle here that we're going to talk about that is important to why we are able to exist. I think that's a good reason to do this work. Cosmic rays are basically the nuclei of atoms. Okay, so take any atom that you know, carbon, oxygen, iron, strip off the electrons and give that nucleus that remains a good solid kick up to close to the speed of light, and you've got a cosmic ray. It'll bounce around in the galaxy. Now, when it gets, some of these reach the Earth, and we put our detectors up there and measure the ones that pass through it. But when they reach the Earth, they hit the atmosphere. They will break up in the atmosphere by hitting, the air itself, other particles in the air. And so my instruments have to get above the atmosphere to do that. This video here shows you, though, some ground-based evidence for knowing how cosmic rays are hitting the top of the atmosphere. This is a spark chamber. You can also do this with a cloud chamber. You can actually see muons, which are the result of all those interactions at the top of the atmosphere, penetrating the whole atmosphere to the bottom here. You've probably heard that pilots have a higher radiation dosage. They get a higher dose than people on the ground. That's because radiation comes from outside the Earth. Right? So we don't use rockets, right? You know that rockets go into space. We use high-altitude balloons. They're filled with helium, and when they are fully at float at about 110,000 feet, they expand to about the size of the inside of a football stadium. So you could nestle it right inside of your favorite football stadium very nicely, right? They are launched from places that are very, very remote. This picture right here is one that I took one of those times I was in Antarctica, of a balloon launch down there near McMurdo Station. And of course, Antarctica is very good for these kind of launches because it's very, very empty. Just like when they launch rockets, they mostly do it from Canaveral out over the ocean, which is very, very empty, right? This is all for safety's sake. Now, my project was actually launched from Sweden and was supposed to come down to Canada. Well, we did make Canada. Although Shauna won't have none of that. None of it. I got to get that right. You can use that. So Canada, which has been in the news lately, you're familiar with all the population centers along the border here, right? Vancouver, let me try that again. Vancouver, Montreal and Toronto here, but there's a vast portion of Canada that's way far up north, and the Northwest Territories, none of it over here, but there's parts of Canada that don't actually make your map very often. These parts is, Canada stretches almost to the North Pole, okay? And these sections here, it goes from the continental part into this vast archipelago, a group of islands, okay? The seventh largest island in the world is the northernmost part of Canada, called Ellesmere. That's where I was. I was down in the tip right down here, where the end of the arrow is. We're next to Greenland here, also in the right? The reason that I ended up in Ellesmere is that because that's where the instrument came down. Its starting point was Kiruna, Sweden, which is right at the Arctic Circle in the north part of Sweden. NASA uses a European launch center there for balloons, right? Special purpose built, and both European and US groups will launch balloons there. Those balloons will go out over the North Atlantic across Greenland and typically land in the northern continental part of Canada. Not my balloon, right? When you send a balloon up, it follows the winds, right? Just like any little helium balloon that you have here. The winds were fairly contrary for us, but while it did at least take it away from Europe and over to Canada, it had a little northerly component. And what started off as us guessing continental Canada turned into Baffin Island, turned into Devon Island, turned into Ellesmere. We turned out to be the northernmost, by only 6 miles, the northernmost detector instrument ever to land at NASA sent up. So we won an award. So let me tell you a little bit about the process of getting Helix off the ground. This is the Helix instrument ready for flight. It's hanging from a giant crane. For scale here, this is a person in the yellow vest, and there are vehicles here, right? This is a very massive instrument. It weighs close to 6,000 pounds just by itself. It hangs from this giant crane, and you can see some wire rope leading off here. This wire rope goes out to a parachute and the balloon itself, and you'll get to see the launch of how this goes. Helix launched on May 28th and came down on June 3rd on Ellesmere Island, so six days and 8 hours or so. Okay. Now, I've got a video here of the launch itself, and hopefully you can hear some sound out of this. This is really tricky. But what you'll see here is the balloon. You can see this long bit here between the balloon and the instrument over here. This is all balloon here. So let's see. Can we hear this? That is the sound of the fabric of the balloon in the wind, right? It is a lovely sound to the person whose science depends on that sound. Now, let me tell you a little bit about what we have here. This is a pre-deployed parachute, okay? So it doesn't pop out of the sack. It's already out. Going down with wire rope down to the instrument. You see the balloon here, but you say, that's pretty small. That's because all this to the top of the parachute is also balloon, okay? And it'll expand when you get up to the higher altitudes, okay? There is what they call a collar here on the bottom here to keep the helium in the top as the helium balloon rises so that it doesn't fill the bottom here. That makes it so it doesn't work. The crane will move around to maneuver underneath the balloon so that when they pull the pin to let the instrument go, it doesn't go across the ground, it goes up. Okay? Now, hopefully here we can hear them prepare to launch it. Talk about removing the collar. And here we go. There we go. All right, so you will see how the balloon just opened up? Okay, that was when the collar let go. You can see a tiny piece of white here, and it's hard to see. There's a smudge here. Oh, there it is. It just went right down here. There's a black thing. That is an aluminum collar that you hope doesn't land on you if you're down on the bottom. Yeah, but there goes it. There goes the instrument. It just got launched. They pulled the pin, and the balloon pulls it up. 2 hours later, it's at 110,000 feet.
Wow.
Yeah, it goes up fast. I mean, think how fast, we'll talk about how high 110,000 feet is right now. As soon as I show you this next video, this is a cartoon of the Helix flight using satellite images of the ground that it went over. I gave Krista Spates, the NKU planetarium director, our GPS track, and she turned it into this image using satellite imagery in a cartoon of the Helix instrument. You can see here some images that were taken by GoPros that we had sitting on the edge of the instrument for the first couple hours until the batteries ran out. But here's the instrument going over the North Atlantic. 110,000 feet, over 20 miles, right? What altitude did jets fly? 35,000 feet, right? What altitude does a U-2 fly at? About 70,000 actually is what I've heard, right? So this thing is way higher than all that, above 98.5% of the atmosphere. Ah, here we go. We're coming down now on Ellesmere Island. NASA cut down now because you could see over there was just a lot of water, right? So this is the last chance to come down before we ended up in the drink. And Krista has it coming down there. Now, I want you to look very carefully here. There is a small speck right there. And if we zoom in on that speck, that is actually the Helix instrument. Interestingly, this image was taken in the month between when the instrument landed and when I got up there and took it apart and out of the field, right? So for the time being anyway, Helix is what people see when they look at these GPS coordinates, if you should ever have a real reason to do that. Pretty cool, pretty nifty, yeah. Now, let's stop talking about Helix and let's talk about me, right? My journey last summer, right? I started in Cincinnati, and of course I participated in preparing Helix for launch. So I flew over to Kierna. I spent about a month there, helping get the instrument put back together after we sent it in a shipping container, doing all the testing, make sure it was working right, because we only had one shot at this. And then I came home, and 2 weeks after I came home, Helix was launched. A few days after it landed, I started heading north through flying commercially through Vancouver to Yellowknife. Yellowknife is a town where you start off the points further north from there. It's about as far north as commercial flights really go until you get into the iffy airlines. From Yellowknife, I took a NASA plane, a fast Cessna, to Cambridge Bay and Resolute. And you have to realize, north of Resolute, there's no more tarmac. All the airports have gravel runways or dirt runways, okay? So it's very different here. In Resolute, I took a smaller plane over to Grise Fjord, this tiny little town. And from Grise Fjord, we took a small helicopter the last 110 miles up to the glacier for the recovery there at the Hadn't landing site. So I wanted to give you a sense of some of the towns I passed through, spent some time in, because this took close to a month for all this to happen, right? Because there's a lot of hurry up and wait. A lot of hurry up and wait. So I spent about a week in Yellowknife, almost a week in Resolute, a week in Grise Fjord before I got out to the payload, a week in Grise Fjord afterwards, another, just time and time. It took me, the whole thing was 2 months. Anyway, Yellowknife is a very pleasant town. And I highly recommend, if you have the opportunity, you want to see some northern lights, go up there when it's not the 24-hour daylight period. Very nice. And go up there when it's not buggy. But the big tourist season for them, for the northern lights, is August, September. It's quite a pleasant town. It's got an old town here, it's on a lake, it's got public art, it's got tall buildings downtown. It's even got an Ethiopian restaurant, one of the best ones I've been to. That's pretty neat, right? Resolute, we just filled up, we just refueled in Cambridge Bay, so I don't really have any pictures of that per se. In Resolute, this is my first Inuit community. Up there, there's about 250 people, no, 400 people, this is right. 400 people, Inuit that live there. There's a lot of services for science crews and whatnot, so there's dorms as well. But you have to realize the houses that are built there, this is permafrost, so they're on beams, right? There's no foundation, so you can actually drag them around if you needed to. The dorms kind of look like this, right? This is, I think my window is on the other side, so I can't point it out. We're on the Arctic Ocean, so walked around, took a look at the Arctic Ocean, still some ice remaining in the June, right, is melting, but there's still a lot there. And the ice that was on the land was melting, and there were a lot of streams cascading down. It's really gorgeous. Lots of clear water there. There was a spot along the shore there where there was a carcass of a beluga whale, I was told, right? And there's an interesting story that goes with this. This happened in the spring, just a few months before I got there, maybe just a couple months. And all the polar bears were very hungry, right, after the winter. They came down, there were supposedly about 40 polar bears there. munching on this carcass, right? Getting in fights. So you see, anyway, they had to put one of the polar bears down because it got in a fight and lost. And this is what remains. But this is one of the first things I saw walking around in Resolute. I was just like, oh, polar bear skin. Is that cool? Or what? You know? The thing is that this is a subsistence community, right? They go out and they hunt for most of their food that they have. And so you'll find a lot of caribou skulls up top. They save the antlers. They can sometimes sell those and get some money. There's musk ox skulls and whatnot that they set up so that the wolves and fox don't get to them. Right? And dogs, they have dogs in town. Grise Fjord, one of my favorite signs ever. Right? Polar bears and musk ox. Maybe in the area. Well, I didn't see them down there in Grise Fjord because it was a long time here, but it was great to have the sign. Grise Fjord is up in the distance here. It lies between this escarpment and the sea, in a very narrow strip of land. Because of that restriction, it's got a very small airport, which is why you can't just fly any plane up there. It's why it was so hard to do this recovery, because we had to use small planes in this last part. But you could still see icebergs out on the sea, right? And here's a picture of the town itself. You can see there's not much to it. This is most of the town. There's a few houses on the left and the right here that are out of frame. You see the government building, the co-op. Every Inuit town has one store, and that's the co-op. My hostel, because it was no hotel, it was more like a crummy dorm. I spent 2 weeks there that I'll never get back. There are 9 rooms, and not a single one of them is really very nice. But it's right here on the shore, and so we could walk to the airport. On the shorelines, the ice it was in the melting phase, right? Because summertime was coming, and so the tide would go up and down, and the ice would break apart, and so you got these fantastical sculptures. Right? The co-op itself was very interesting. I spent a lot of time in there because there's nothing else to do in town. You just wander and look at things. It's got shelves full of barbecue sauce and ketchup. And, which goes well with seal, I'm told. But I'm not sure. I've never tried it. There's also some staples, like rice and cereal and milk and whatnot. And a lot of the prices are subsidized, but a bag of chips is $15. That's not subsidized. So you can also buy fox furs, right? Locally caught. You can buy a range, an oven, and a couch, loaves of bread here. You can buy wool for knitting. As long as you want this range and that couch, you're in good shape. Not exactly as much. This is the view from my hostel window, which I should say dorm window. Let's just call it that. Not much to see. The airport is up behind the government building here. You can see how these escarpments are just right there. Right? This is the view from inside the airplane as we were approaching Grise Fjord. And it's like I wanted to lean up and say, guys, are you gonna go up or turn soon? Yeah, but it turns out that the weather has to be just right to come into Grise Fjord because you have to see, not to hit the mountains, because you come in straight at the mountains and you take a quick bank to the left and down you go. It's pretty frightening, actually. And this is the airstrip. It's only 1,500 feet long. As you see, it's dirt. A short airstrip like that is only handleable by one kind of plane, and there are reminders that it's still not particularly but that plane is the workhorse of the North, the Twin Otter, right? This has been around for a long time, and you can put pontoons on it and land in lakes. It's really quite the plane. It's got a very small capacity though, weight-wise. Given the distance we had to go back and forth to Resolute, this plane could carry about 2,200 pounds extra, And every passenger is counted as 300 pounds, no matter how much you weigh or your gear, right? It's just, you're just 300 pounds. Airports up there were just little passenger terminals that people kept warm in. That's it. That's all they were. It wasn't anything special at all. There was no restaurant, nothing like that. You just got in there and just hung out. I did get a picture of the Cambridge terminal because I never left the gravel tarmac out there. I just hung around while we refueled. But they all had somebody to talk to in case you needed to make friends. Or at least check out what a musk ox looks like up close. I've never seen one before, so it's pretty nifty. But this is the surprise. The flowers in the Arctic are amazing. Just incredible. There are these vibrant purples, and they're against the stark gray or brown rocks there. So they just pop like crazy. And this was close to high summer in the Arctic, so they were, really all out and ready to go. But you had purples and yellows, and you also had the mosses that were on the low-lying areas and short grasses. Just amazing. I'm a flower aficionado, and every time I see a flower, I have to take its picture. And my camera, I don't have any room left on my Google Drive because it's full of flower pictures. I just loved all this. I'm very happy. So let's switch to the instrument field recovery now. Let's go out on the glacier. The conditions out there, we had 24-hour daylight. We were located on the glacier. We were only able to get out there with a small helicopter. The weather was very, very important. To give you an idea of some of the issues we were having, you can download this app yourself on your phone. This is a screenshot from my phone of the windy app, and the pilots loved it. They said, oh, this is just how we can do the weather right here. Okay. This is the outline of Ellesmere Island on here, Grise Fjord. I've marked here with an overlay, and our payloads up here. You can see by the colors what the winds are. So the very red is about 40 knots. This is about 24 knots up here. Down in Grise Fjord, we were hanging out here. It's too windy to go to the payload, so we're just hanging out, doing whatever, reading books. I read 11 books in Grise Fjord, so to give you an idea of what I was doing. The wind was so wild and crazy. 40-knot winds are a lot. Sometimes the gusts would be high enough, and I'm guessing 60, 70 knots. But because these buildings didn't have foundations or anything, they did a lot of movement. And they didn't, I'm not sure they exactly tipped, but it sure did feel like it. And I don't know if you guys have ever seen Jurassic Park, but there's a scene in there that was exactly what my water glass is doing when the Tyrannosaurus Rex is coming. Right? Boom. So like that. So the gust would hit the side, and my water glass is doing that exact same thing. So it was pretty fun. I thought I'd share with you some of the pictures that things I saw from the helicopter while I was going through the field. We had an aborted attempt to go out to the field on our first day. And I just was taking pictures like crazy. This is a view out one of the fjords as we were flying over. You can see out to the ocean out there. You can see that the ice is melting. We saw a little cluster of musk ox in that first day. The scenery was spectacular. Here's looking over that same fjord. The landforms, how does that happen? That is not volcanic, I don't know. It's incredible. Up and you can see the glacier in the background here and sort of the cloud bank as well. Just in other parts of it, you can see this sculptured earth that you get up there where the land is bare. And the wind, the rain, the melting snow, right, formed this incredible things after a while. Because all this was just like covered in glacier, tens of thousands of years ago. And all this is really formed lately. Glaciers really fantastic to see how they tumbled off of the high field into into the fjords. You can see them coming down. Here's one that's like a river of ice into the fjord itself, dumping into the fjord. This region here where it's all broken up, a little bit better of a close-up. You can see the detail, the cracks and crevices in there as the ice would tilt and break there. The scenery that was really breathtaking was up on the glacier itself the next day when we finally made it. I just threw this in here. You'd have these mountain tops peeking out from between the ice, right? And just incredible, really delightful. When we finally did make it out there on our first day, we parked the helicopter close to the instrument and sent a couple guys out with sticks and tied to ropes in the hopes they didn't fall down a crevasse. And they didn't. So the rest of us followed, and we went out and we started taking the instrument apart. When we got out there, we looked at it and we said, oh, look, how lucky for us. It's not covered in snow. Because usually, if something sits on the ice, on the snow like that, then it's going to blow over, it's going to start burying it. And I've dug many instruments out of snow in Antarctica. It's standard. The snow was on the inside. Yeah. All it takes is a tiny little crack. People who live around deserts know this, I think, really well. That it doesn't take much for the sand to get in. And the snow's the same way, right? Got all over the electronics and stuff. So our shovels did come in handy after all. We dug out the insides instead of the outsides. At this point, it was time to start lightening the load. We had to take this instrument apart. We had to turn 6,000 pounds into enough loads to get home on the helicopter, which could only take 2,000 pounds, and that includes the passengers. We wanted to go home. So not much, right? So the primary tool that we used was what was called a chop saw. This is a gas-powered friction saw. It's just it's not a blade with teeth on it. It's just a blade that chops through things like butter. Okay, you're grinding wheel. Okay. We got our priority items out first, like the data disks, right? So we can go home at that point and have a successful mission. Here's a picture of little detector bits. This is the tracker inside the black magnet here. We used snow as one of our tools, built a ramp out, and we would slide out the tracker and move on to the next part. So we had all that. At the end of the day, we loaded our helicopter with some of our more priority items to get out. Here's a picture of the mess that we made, and went home, right? Happy campers with pieces of the detector in our laps, right? The next day we came out, we can see that we have a mess spread around, but what's really key here is that the frame is still in one piece. This is about a 4,000 pound item right there, and we had to divide it in two at least to get it home. So we started working on that using, again, this chop saw. There were 4 uprights. We spent the previous day separating all the cables from the top and the bottom sections. Sometimes you can just use a cutter. Sometimes you want to save the cables. And we would cut all 4 of those. The idea was that we could pull the piece in the back so that it would stand up, drag it out of the way, and use the top one to then drag it over, because we wanted both of these parts to fall in the upright position. That's not the way it worked. The bottom part did, in fact, fall the right direction. The top part fell on its belly and was with its feet up in the air. Turned turtle, I think is the expression. Yeah. And we had to turn that over. So fortunately, I was in charge of recovery, and I brought the best tools. Spent a lot of money on good stuff. And one of the things I took were heavy-duty straps and come along. The come along is this thing that you crank to make whatever's going over there attached to the other end of the strap to come along, right? And in fact, it worked brilliantly. We were able to do 2 rolls, roll 1, roll 2, and have it standing up so that in the end, it was just there ready for the helicopter to pick that up. We had 2 pieces. The other part was light enough. We threw a bag of very expensive high-tech trash on top of it. And then we had a pile of aluminum over here that we still have to sort through, but maybe we'd let the pilots do that. We'll see. The pilots did, in fact, take over at this point. They had pulled, while we were doing the rolling of the instrument there, the pilot and one of my team had loaded the helicopter and taken one load down to Grease Fjord, emptied it, and come back. Right, so that took about 4 or 5 hours. We were out in the field by ourselves. we were not concerned. It was so beautiful. I mean, you know, what's the worst thing that can happen? Have a chop saw cut off an arm, or maybe have one of the pieces of the instrument roll over on this. I mean, polar bear, yeah. Hungry polar bear. Isn't that a child's story, right? But we, you know, when you hang a very heavy item like this from a helicopter, there's a lot of air friction, and the helicopter can't go as far on a single tank of fuel. There had to be fuel caches every 50 miles. And so the pilots spent about 4 days setting up this fuel caches. So, for example, between Grease Fjord and our payload, there was one fuel cache. It consisted of 2 fuel drums, which they would have to bring back. They have to go drop them off, go to the payload, pick up half of the payload, come back, fill up with the fuel, bring the payload back, go back to the fuel cache, bring the drums back, fill them up, go out to the field, drop the drums off, go up, pick up the next half, come out, fill up, back, go out and get the drums. All right, that was one set of movements. Then they had to do that heading to Resolute. Now, Resolute was 200 miles away. So how many fuel caches is that? Every 50 miles? 50, 100, 150. 3 fuel caches that they had to have. These guys were busy. They were out so much that the co-pilot, they had the bubble in the front of the co-pilot came in that evening. He was completely sunburned, sitting in the front. Right, I had to lend him my sunscreen. Right, but we got all that stuff back, and we were really happy. Did the victory dance there in Grease Fjord, and started the process of getting it down to Resolute. There were 2 types of things. The pilots were taking the 2 halves of the instrument, and we had all the pieces that we had taken off to lighten the load. These were going around in our $400 a day truck rental. This is from a private individual, yeah. And we were storing it in a garage. This is in contrast, right? We also made a bargain with the guy that he said, "Yeah, okay, I'll let you use this garage space, but I want 2 cases of Fanta and orange and 1 case of Pepsi." I said, "Okay, we can do that." So we brought that up because in the co-op, that stuff is pricier than gold. Yes, right? It is not a subsidized item, and everything is air freighted up there. So we, here on the right, you can see where we've loaded the Twin Otter finally to get out of there. This is our last trip. I had it all strapped in. We sat in the green chairs, off we went. In Resolute, we had a large cargo plane chartered from Yellowknife so it could make the hop in 1 trip. It had a little conveyor belt. We could load up our pieces, push them towards the back. The crew on this airplane, this large cargo airplane, was able to dump the stuff on the tarmac in Yellowknife back to the land of pavement. And we came in and we went over, we drive over in our SUVs and trucks, we pick it up and bring it back and load it up into our sea container. And all of this took 44 days from the time that the instrument landed to the time we closed the door on the sea containers because of logistics. That was the primary driver, right? When can we get the hostel rooms up in Grease Fjord? When can we get the airplane reserved, right? All of this stuff. Why is the weather so bad? Right? All this drove our timing. But in the end, you have to ask the question, why? Why work so hard on something like this? The idea is that we can fly this instrument again, okay? And trust me, this is a Humpty Dumpty instrument. But here's what we're going to talk about with the science question. So this is part 2 of the talk. We're going to shift from pretty pictures of the North to a little bit of science. Right? So here's the periodic table right after the Big Bang. There are basically 2 elements, hydrogen and helium. A tiny, tiny, tiny bit of lithium is poking out right there. But it's really just a hydrogen and helium universe. None of the things we need for life exist. Oxygen, carbon, iron do not exist. This is the periodic table as we know it now, right? Richly filled in with a lot of variety, right? Very large. Where did all that stuff come from? Well, the short answer is that stars are the crucibles in which new elements are formed. And I'm going to take a few minutes here and try to explain how that works. The process of stellar nucleosynthesis, it uses fusion, right, as opposed to fission. Fission is uranium bombs, fusion is hydrogen bombs. Fusion to take hydrogen and fuse it into helium, and then fuse helium together to make carbon, fuse helium onto carbon to make neon, and then oxygen and silicon. And you can use this process of fusion to drive stars' energy, right, keeping them shining bright, until you get to the point where you've created iron. And iron is as much as you can burn in the fusion process and get energy out. So the most massive stars in our galaxy have cores that are iron. Stars like our sun will eventually have a core that is carbon. That's as far as it'll get. It's not big enough to create the heat and pressure that's needed to burn up to iron. Okay, but I want to take a minute. I found this graphic and I thought this is really fantastic. This happens so quickly for these massive stars. They burn their candles at both ends. Right? That hydrogen fusion takes several million years. But look at how much shorter everything gets as you move down here. And that silicon burning to form that iron core ash, 1 day. That's phenomenal. Just happens so quickly. Very massive stars, very hot, very fast. So that big iron core forms, and it grows so quickly, at some point it can't support its own weight, and it collapses. It collapses into a neutron star or a black hole, and the rest of the star falls in as well. And then it bounces. And that bounce is what we call a supernova. That is what massive stars do to end their lives. When they reach that iron core tipping point, and that supernova will spread all of these different layers that were here out into space, so that you have a seeding of the space between the stars, the interstellar medium, with new elements, right? Because this star started off as hydrogen and helium, and now look at all the stuff that's created. Stars are the crucibles in which new elements are formed. There's other processes besides the fusion process that can give you new elements. So you can ask, well, iron, that's only half of the periodic table. What about all the heavier stuff? Well, really good question. I could tell you to ask that. There's a process called neutron addition, and this is since there's a lot of loose neutrons in stars as part of the fusion process, they can hit into get a seed nucleus, for example, an iron nucleus, and make it heavier and heavier and heavier by adding neutrons to it. Now, occasionally there'll be a radioactive decay as the nucleus gets heavier and heavier. It's not stable, and one of those neutrons will turn into a proton. So adding neutrons works your way out to the right here, and as you have radioactive decay, you work upwards. Now, to the right is a heavier and heavier nucleus. To the upwards is higher and higher on the periodic table with higher and higher charge. Okay. So that neutron addition is working. And this example is just going from silver to tin, but you can work your way up through that process a lot. Another source, very exciting, binary neutron star mergers. So a binary neutron star system starts off as two very, very massive stars that go through the whole cycle, both with supernova, and we're left with two neutron stars revolving around each other. Okay, and they spiral inwards until they hit each other and merge. Right now, there's a lot of it's a big boom at that point. A lot of energy is released. You can get a black hole in the middle, but then a lot of stuff goes spewing outwards. We know these exist because we have detected them. In 2017, the LIGO experiment detected the first gravitational wave binary neutrons from binary neutron star mergers. And the people working on that got the Nobel Prize for that work. Right? It's phenomenal work. Really hard to do. And that will only get better and better. We have a new way of looking at our universe now through gravitational waves and seeing different kinds of things. One of the mergers that they detected that year, because by the way, there are a lot of these going on out there. Nobody even thought it was as common as it is. Created a lot of strontium. You can look at the visible spectrum, the X-ray spectrum, and you can see lines associated with the element strontium, which is very, very high on the periodic table, far above iron. And it said that there were about, the strength of the lines was such that about 5 Earth masses of just strontium, okay? and it was propelled away at about 30% the speed of light from the center of the explosion, right? So this is an extremely violent process. So where are we? All right. New stars are formed from the detritus of dead stars, right? You have nebula, and those nebula are really what used to be stars that might have gone supernova. There's beautiful nebula when you look through an optical telescope. There's star-forming regions like the center of the Orion Nebula here, in the very center of here, there's some bright spots. Those are very, very massive stars that have, the short lifetimes, like we're looking at the previous ones. You may see a pretty picture here, but I see the galactic matter cycle at work. Here's a graphic to tell you how this kind of works in a very simple, quick way, because we want to be quick. Take a nebula, start making stars out of it, right? Parts of the nebula collapse, you get a new star. Some of them are big, some of them are little. The big ones, is very exciting. They'll form this in the course of millions of years. They'll go supernova, end up as a neutron star or black hole, and spew most of their mass back into the interstellar medium, right? That neutron star or black hole does not represent a very high fraction of the mass of the original star. On this other side, a sun-like star, a less massive star, can form. That takes billions of years. Our star is about halfway through its life cycle, burning hydrogen. It's about 4.6 billion years old. And it's got about that much further to go. So there's a lot to go. But when it finally turns into a red giant, it will pulse and throw off its outer layers, and most of its mass goes back into the interstellar medium as well. Enriched with new elements formed in the process of fusion as that star burned hydrogen into helium, into carbon, into oxygen, into nitrogen, etc. So this is how the periodic table was formed filled in from what we saw after the Big Bang of only hydrogen and helium. So this process of creating new elements in stars and returning those elements to the next generation of solar system is the galactic matter cycle. And another phrase is the chemical evolution of the galaxy. Right? You can think of that. Right? How we got from one kind of chemical constituency to another. So our solar system, as I mentioned, was formed from interstellar gas and dust about 4.6 billion years ago. So it's a snapshot of what our galaxy's chemical composition was at that time. And it's reasonable to ask the question, well, 4.6 billion years, that's about a third of the life of the universe. That's a long time. How has the galaxy's chemical constituency changed since then? I mean, it's reasonable to ask the question, have there been changes, right, as this galactic matter cycle progresses? And this is where cosmic rays come in, because cosmic rays are pieces of matter from outside our solar system. So we can compare what we measure inside the solar system to these cosmic rays coming in from outside the solar system. But we have to understand these cosmic rays really, really well, right? And this is where the helix will come in, right? So here's a little, another movie. This one, here's a massive star about to go supernova. Don't miss it, right? So supernova comes. And what you see is a big shock wave, right? This is a classic way that you see what's going on with the supernova. And I want you to understand exactly what's going on here. I want you to think of all those action movies that you've watched where you've seen, a bomb go off somewhere. And you see stuff flung around near the center of the bomb, but then there's a shock wave that breaks everybody's windows, right? This same sort of thing is going on in a supernova. All the matter that's flung off of the star is still in the center here. But there's this beautiful glowing bit that's way around the edges. That's just a shock wave. It's just like that sound pulse that goes off from the chemical explosion in the movies. This is traveling through the gas and dust of the interstellar medium, right? Much more rarefied, less, close to a vacuum, but not a perfect vacuum. There's enough material in there that it really does create a shock wave. And it heats the material up, and heated material will glow, just like those like the flame in your gas stove or the electric burners, which heat up and they glow. Let's see if I can get, nope, there, okay. So here's where cosmic rays come from. The interstellar medium itself is what the shock wave propagates through, and the shock wave is so violent that it can accelerate cosmic rays up to light speed. So it'll strip off their electrons of these atoms, okay? Take the nucleus itself, which is now charged, and charge is like something that magnetic fields can grab onto and fling it up to, and electric fields, and fling it up to light speeds, right? And then it'll propagate around the Earth and finally get to us. Here's what that looks like. So we have the life of a cosmic ray when you have production and acceleration up in a supernova remnant, and then there's this process of propagation. And this takes 6 to 10 million years, somewhere in there, and there's a lot that goes on here. First of all, cosmic rays aren't traveling in a straight line because the galaxy is permeated with these very weak magnetic fields that cause it to bend. Now, there's vast distances here, right? Light years, hundreds of light years, thousands of light years. And so a weak magnetic field can cause a lot of bending, okay? The other thing that happens is a process called spallation. And this is when the cosmic ray meets a gas atom, okay, in the interstellar medium, and it breaks apart. So say you're a hydrogen atom just minding your own business, and suddenly this Mack truck comes and smacks into you, right? So a carbon atom will smack into you and break into a part. The carbon atom can turn into a boron and other stuff. That boron will continue as a cosmic ray and possibly get detected here on Earth, for example. So what we see here at Earth is not what was launched back at the supernova. We have to be able to unfold this process before we make any statements about what the difference is between what's here on Earth and the solar system and its composition and the rest of the galaxy. That unfolding process is pretty important. We still have other things that happen to that poor cosmic ray. It's got to swim upstream against the sun's magnetic field, and then finally it's got to swim up against the Earth's magnetic field, and finally when it reaches the atmosphere, it's completely obliterated, but we try to get above the atmosphere to measure it. So here's where helix comes in. The galaxy, it's remarkable. This is a very simple model and it works really, really well. You can think of the galaxy looking like a box to a cosmic ray. Just a big box. And you have a source of cosmic rays, like a supernova explosion, and these cosmic rays go outwards, and they start bouncing off the sides of the box. And in the process, they lose all sense of what their original direction was, right? And they're, what's called, the word is isotropized. That means that if you were to stand out in space and look at cosmic rays, if you have that kind of vision, right, like Superman, you would see the same amount of cosmic rays coming from every direction. Okay, and this is how we know we're in a box. Because if we weren't in a box, the cosmic rays would be greater where there were sources, because we live at the edge of the galaxy. There would be more cosmic rays coming from the center of the galaxy, where there's more supernova, for example, than out from the edge of the galaxy, and we would see a directional bias with the cosmic rays reaching us. But nope, we live in a cosmic ray box, okay, the size of something. And that's where helix comes in. How big is this box? Helix is designed to make the right kind of measurements to determine that. And you may say, well, wait a minute, I can look in the sky and I can see how big the galaxy is. But that's the galaxy according to stars. The galaxy according to cosmic rays doesn't depend on starlight, it depends on those weak magnetic fields. And we know that they leak outside of the plane of the galaxy and form a big halo around the galaxy itself, but we're not sure exactly how big. So that's what helix is designed to do, and the technical aspects of how that's done is not something that I'll go with right now. I was warned against that.
Darn.
Yeah, right. But I want to leave you with a picture of the periodic table of the elements written out in a different way. Right? This is taking where the elements come from, the origin of the elements. So in this picture here, it's hard to see the colors, I'm sorry about that. But the Big Bang is sort of a light blue, and you can see that there's hydrogen and helium is mostly that color. Now this cosmic ray spallation is a different color. That is hard to tell from the light blue, but take my word for it. It looks different up here on my screen. Beryllium and boron are all this color of cosmic ray spallation. In other words, here on Earth, if you hold a beryllium atom in your hand or a boron atom in your hand, once upon a time, it was a cosmic ray. And not just any cosmic ray. It was a cosmic ray that smashed into some other atom and spallated. It would have originally been a carbon or an oxygen or an ion or some other probably common thing, right? All the beryllium and boron in the universe comes from cosmic ray spallation because beryllium and boron are not part of the fusion cycle in stars. There's other elements like this too, what we call the sub-iron elements that are just below iron, and cosmic rays form some of those, but there are other ways to make those kind of elements as well. So this whole line here from potassium up to iron, NK potassium?
Yeah.
Yeah, okay, yeah. I know there's some chemists in here, right? This whole region up through here, you can form the sub-iron region, and they're not part of the stellar burning process. There's a lot of skipping between silicon and iron that goes on. There's other processes here. The exploding neutron stars is supposed to be in green. This is really the binary neutron star mergers, and this is the green that you have here. Forming these heaviest elements like thorium and uranium. There's also the rapid and slow neutron addition processes, or what they're calling the low mass stars, and the exploding massive stars. So there's lots of different ways that the elements are made in our understanding at this point, and it required all these processes to get to the point where we all are today, where we have this full table here. And as the galaxy evolves chemically, we'll have more and more of this. Now you may ask, how much do we have at this point? Because right now our world looks like it's full of the heavy stuff, right? This is still random. The universe, our galaxy is 90% helium, hydrogen, 10% helium. That doesn't leave anything else, does it? Right? Actually, in reality, it's about 1% everything else. Okay, so the stuff that we're used to is still the minority in terms of what's out there in the galaxy. Okay, that will increase. Give it enough time. The galactic matter cycle goes on and on and on. The end. Thank you. While you're getting ready on that, let me just say one thing. The NASA balloon program, I was cleaning up my office because we're getting a new science building, so I have to do some cleaning. And and I found some little sheets on the NASA balloon program. These are available for you to pick up tonight as you leave. There's not enough for everybody. So please, if you're going to pick one up, please read it.
All right, folks, well, we have about 10 minutes for questions. If folks would like to come up and ask them, I know we can hear you, but as we've learned, our friends online cannot. Those who are online, of course, can send us messages to my pocket, and I will also ask Dr. Nutter for us. So with that, I open the floor if someone has a question.
Fascinating. Okay, let's see if I can frame this. I understood that you said the periodic table of the elements as we know it is from what was fusion, but from the beginning of our solar system. Is that what it was?
In the Big Bang, there's just hydrogen and helium, and everything was built up since then in stars.
So my question is this the periodic table of the elements as it is now? Can it change in the future, or would it be possible to have a different periodic table of the elements in, say, different galaxy long, long ago, far, far away, or whatever?
Yeah. So that's a good question, and the answer is yes and no. right? As far as we know, it's not possible really to create any more stable elements. Okay, there's a theory that there should be a little island of stability way, way, way out there in some heavy things, but we can't seem to get it to work out in experiments and the colliders where we're trying to produce these heavy elements, and we're not finding any evidence that these sort of things exist. Right? People look for this stuff. So we don't think there's any more elements out there to form anymore. Now, the reason our periodic table is full right now is that it's been 13.6 billion years or so since the Big Bang, and there's been a lot of this galactic matter cycle stuff going on right now, and we're in the phase where we're just making more and more of the heavy stuff, not adding to it. Close to in the beginning, right, there would have been this sort of gentle filling in of the periodic table as new stars were born. There's probably, just starting with the first short-lived stars, and they would have gone off and formed everything up to iron, but there wouldn't have been any seed nuclei to make the bigger stuff until the second generation of stars, and then the iron that was out there in the cosmic rays could have been in the rapid process, brought up to more. So the answer of yes, it's possible to be different is if you go back in time. But the answer no is in space right now. I think we've pretty much got it, and I think going forward, there's not going to be any changes. I could be wrong, but I don't think so. Other questions? Come on up. Just come on up and make a line.
I just have a question for my 5-year-old brain.
Okay.
Why not just launch a balloon in Minnesota and pick it up on the Jersey Turnpike?
Yeah. Well, it's a safety thing, right? I was saying that we like to launch these balloons in very, very empty places just in case of accidents. There is a hole in a field in Nebraska where there was an accident and the payload fell 110,000 feet.
Is it a big hole?
It's an old hole, but it's about as big as this. I knew the folks who were on that experiment. It was a precursor to this experiment.
Okay. Other than having a big empty space, was there a physics reason for going there as far as collecting particles better or different, rather than in Minnesota? That
is a very good question. The answer is for us, no. People who do solar physics like to get up towards the poles so that they can look at the auroral things, and then you don't see that in the equator. For us, no. Come on down.
Thanks, Scott. That was really interesting. We went to all this effort to retrieve the instrument. I assume that there's a Helix 2.0 in the future. What are the goals of that project going to be, and how will you modify your instrument to achieve those?
Okay, so it's going to be the same science goal in the sense that we're measuring this obscure, actually beryllium. I'll tell you what we're measuring in Helix. It's 2 isotopes of beryllium. We want to get their ratios. One of the isotopes is radioactive, the other is not. They're the same charge, so they propagate through the magnetic fields the same way. But since one's radioactive, as it propagates, it'll decay. So it's a clock. So we have a measure of how much time was actually spent doing the propagation through this clock. Once we get that ratio understood, we have other measures of measuring the distance that's traveled, how much matter was traveled. We have you don't measure actually how many light years you went through. You measure how often there was an interaction, which means how much material you went through. And that's a different kind of statement, right? Because what if all the places you went through were heavy with nebula? Or what if all of them were very, very, like around our solar system, which is very, very empty? Yeah. Right? So unfolding these two things is part of what Helix is looking for. Now, Helix 2.0, we hope will happen, right? We are going to take the data from this flight, get some initial science data, but we always want more. We're greedy for more. Our beryllium isotopes are rare enough that 6 days is not long enough to collect enough of them to get a good solid statement about what's going on. The error bars, the statistical error bars, will still be large. So more flights, smaller bars. In terms of what Helix 2.0 will look like. There are some lessons learned from Helix 1.0 about what we should change for Helix 2.0, and we will incorporate those. We do have to ask NASA for those funds to do it. So we don't have that yet. Right now we're in the data analysis stage, and we will be hopefully reporting on initial results this summer at a major conference. Good question.
So first of all, we have a couple of young scientists joining us, including Wyatt, who's 8 years old. So you might want to shout him out. But while we're talking, there was also a question about how we will know how big our box is.
How we know?
How will we know how big the box how big it is? Like our universe of box.
What? So how big is it? How will we know? Right. So Wyatt is asking basically what I was just mentioning in the answer to the previous question, which is what measurement is Helix making that will help us know how big the box is? It has to do with the clock isotopes and measuring time spent as a cosmic ray versus how many interactions, which is the thickness of material spent. The time, and you can, with the model of how the box looks to a cosmic ray, is model dependent. The answer comes out of plugging in those measurements in there to know how big the box is. So there's a slide that I have. Wyatt, you're going to be sorry about this that you asked. This is the money plot for us, where the beryllium isotope ratio is on this side. This is the energy of the cosmic ray increasing in this direction. These are the different predictions and the existing measurements. The yellow ones are the experiment that went from 110,000 feet. The telemeter data they were able to analyze and get things with big, big, big error bars. This red experiment here is new data that just came out a few years ago, but it was what we call unresolved mass spectra. What does that mean? It means that you're using, you don't see peaks at, this is a beryllium 10, beryllium 9. You don't see a peak at 9 and a peak at 10. You see them smushed together, and you have to say, well, my instrument behaves like this, and I think there's this many 9s and this many 10s. You don't individually identify them, you make a statistical statement. So there's a lot of suspicion about those measurements. So Wyatt, I can only say that the box size, I'll hopefully be able to tell you what that is this summer if you get back to me. But we combine Helix's measurements with measurements from other experiments to finally get that answer. Was there another question from the listeners?
If our sun will not get enough iron and collapse, what will the end of the sun look like?
Yeah, so we won't have an iron core. Our sun, being a low mass star, will end up with a carbon core. And it's if you go back to the galactic matter cycle, it will be one of those low mass stars that lives billions of years and ends up as a white dwarf. So that white dwarf is basically a big ball of carbon, very white hot, right? That's why it's a white dwarf, white hot. And it'll glow for a long time until it becomes a dark ball of carbon. It just, there's no new energy being created. Okay? All the out material that's on the outside of it will be pulsed back into the interstellar medium. But don't worry, this is still 4.5 billion years in our future. So we've got some time to enjoy the Earth as it is now.
You have time for one last question? If there's anyone in the audience, come on up.
So this kind of refers to your last comment. Does the ratio of all the elements, are they stabilized, or are we eventually going to all end up as? That's the open question. I don't mean we.
So are the relative amounts of the elements being created changing? Yes. Well, that is the question that we're trying to answer. That was, I mentioned a slide that said that the solar system is a snapshot of what the galaxy looked like 4.6 billion years ago. And the cosmic rays are young matter samples. We think they're created within the last 10, 20 million years, right? So very young relative to the 4.6 billion years. How do those look different? And helix is part of the unfolding of what we actually measure back to what the source looks like, back at the supernova. So I can't answer your question yet, because that's the point of the science question. That's exactly right. It's exactly, you've reached the heart of the matter. Okay, good. Thank you very much for coming.
And perhaps a good place to end.
Yeah.
With that, those folks who are interested in taking a tour, we're going to be doing that out this way. For those of you joining us at home, thank you very much. And thanks to Norse Media for all their work tonight with all of the technical challenges and they're in and helping us with all the things. They go with us everywhere for Howard Center, so we're very thankful for them. And so with that, thank you for joining us tonight and safe travels.